Welcome to In 5 Minutes. Let us now discuss the receiver of quadrature carrier multiplexing. Let me quickly remind you that on the transmitter side, if you remember, we had transmitted signal, multiplex signal, which we had called S of t, which was the sum of y1 and y2, the two outputs of the two product modulators. We had used the same carrier frequency, but in both the cases the carrier forms were different. We were using cosine form in the first modulator and sine form in the second modulator. That means both the carrier signals were 90-degree phase apart from each other. Now when we discuss the receiver, we will start from the multiplex signal. So the receiver block diagram is there on the screen. As you can see, it is going to receive the multiplex signal S of t. Now let us quickly write down the proper expression of S of t, the complete expression of S of t. Y1t was output of the first modulator, to which input was M1t AC cos 2 pi fct. That was the form of the first carrier signal, plus Y2t was output of the second modulator, to which input was M2t, and carrier form was sine 2 pi fct. So now you can see we are again using product modulators on the receiver side also. Once again, these product modulators will be nothing but balanced modulators. You may also call them product demodulators because they are used on the receiver side, but the actual circuit that we will use in both the blocks remain exactly same. Now we are once again giving cos 2 pi fct, the original form of the carrier, cosine form of the carrier, to the first product modulator. Let us see what will be output of the first product modulator. The output of the first product modulator, I'm going to call it this time, let's say x1t. So x1t is equal to s of t, which is input, multiplied with cos of 2 pi fct. S of t is this whole thing. Now we will do it in one go. When you multiply s of t with cos 2 pi fct, you can see there are two terms. In the first term, you will have cos multiplied with the same form of cos. So we get cos squared, and I will immediately replace cos squared with its equivalent, which is 1 plus cos 4 pi fct by 2. I'll write that by 2 outside. Cos squared theta is 1 plus cos 2 theta by 2. So the frequency becomes twice of the original frequency. But this is just the first term. In the second term, you can see we have M2t and AC, and sine will be multiplied by cos. So we will get sine theta into cos theta because the angle in both the cases is exactly same. Now if you remember, there's a formula 2 sine theta cos theta is equal to sine 2 theta. So I will use that formula. We don't have 2 here, so we will divide by 2 and multiply by 2. So we get 2 sine theta cos theta, which is sine of 2 theta. So it becomes sine 4 pi fct. So at the output of the first product modulator, we have got three terms now. I will expand the first pair of brackets. We get half AC M1T into 1, so we get the same term as it is. When you multiply with the second term, you get half AC M1T into cos 4 pi fct, and the third term is half AC M2T into sine 4 pi fct. So this is my output x1t of the first product modulator. The output is given to a low pass filter. It is passed through the low pass filter, and the output of the low pass filter is my final output of the receiver. So let us now write down output of the low pass filter. Let me call this output as x01t. So you can see that after you pass x1t through a low pass filter, output of the low pass filter x01t is equal to, first term consists of m1t, which is my first modulating signal. It will have frequencies from 20 Hz to 20 kilohertz, and we will set the cutoff frequency of the low pass filter at least 20 kilohertz so that it will allow the first term to come at the output side. So we get the first output term as half AC M1T, plus, if you observe the second and the third term, it is the multiplication between the modulating signal whose frequencies are FM1 and FM2, and two sinusoidal signals whose frequencies are twice Fc. Because of this 4 here, the frequencies are twice Fc. The overall frequencies, because you are multiplying the two terms in time domain, their frequencies will be added and subtracted. So the overall frequencies of the second term will be 2fc plus fm1 and 2fc minus fm1. The frequencies of the third term will be 2fc plus fm2 and 2fc minus fm2, and there will be all the other frequencies in between those two extreme frequency values. All we have to understand right now is that the frequency values of the second and the third term, because they are present around 2fc, are much larger compared to the frequencies of the first term, which only go up to fm1, which can be maximum equal to 20 kilohertz. And hence output of the low pass filter will be only the first term. The remaining two terms will be blocked by the low pass filter, and hence we say that my output is nothing but first modulating signal. You can see my output is the first modulating signal, and this proves that we can very well demodulate the first modulating signal from the mixture of the two modulated waveforms. We had taken two modulated waveforms, added them, and we were transmitting multiplex signal. So we could extract the first modulating signal, and hence partially we have proved that the quadrature carrier multiplexing system can work perfectly.